Last time we were talking about the Chatelier. My French isn't that good. Let's call him the Chatelier. Chatelier's principle. And for the most part, there's not, why this guy's name got attached to it, I'm not sure. But most of the stuff that you learn in terms of Le Chatelier's principle is stuff that you could derive directly just from looking at the equilibrium constant. And so it tells you things like, I think this is the reaction we were looking at. It tells you things like, what happens if you add more, so you're at equilibrium. So the reaction's not changing when you're at equilibrium. And then it says, well, what happens if I kind of knock it out of its equilibrium state? So if I'm at equilibrium and I add more NO2, how does that affect the reaction? And the answer is just that it pushes it back towards the reactants. And the opposite of that is true. If I add reactants, I push it towards the products. Those are probably the two most important parts of Le Chatelier's principle. Is just what happens when you add reactants or products. So if you change the concentration on one side or the other, what's the overall effect going to be on the distribution of products and reactants? Let's see. The other ones that are more nuanced that we talked about was if you change the volume, for example, when you're with a gas, what effect does that have? And that depends on the number of moles on both sides. If you change this is a gas that we're looking at, so you're talking about volume changes. But if you have a solution, if you dilute it, what's the effect going to be on the equilibria then? And again, it depends on the number of moles that you have. And the last thing to talk about is what happens when you deal with temperature. So let's see. I'm trying to remember if this is an endothermic or exothermic reaction. Yeah, I think if this is an endothermic, let's call it endothermic. So the last thing to concern yourself with, and this is something that you can also derive straight from the equilibrium constants. Well, it's a little bit more, it takes a little bit more work. You have to deal with some free energy stuff. I don't know. This one is the least intuitive. But if you can kind of remember it, since Le Chatelier's principle is really just kind of a shortcut, at least that's the way I think of it. It's kind of a crib sheet for what happens to reactions at equilibria. So if you have an endothermic reaction, like this one, that means delta H is going to be positive. For positive delta H, that means that you can treat delta H, you can kind of make it out like it's one of your reactants. Because you are, in fact, if you are running a reaction and it's endothermic, you're putting heat into, you have to put heat into the system. So it's kind of like heat is consumed. You can think of it like a reaction, like as if it's one of the reagents over here. So you say, okay, delta H is like a reagent because I'm having to put heat into the system to get this reaction to go. And then you can use this to sort of figure out what happens as I change the temperature. So if I increase the temperature, and we're thinking of this like a reactant, then it has the exact effect that increasing the concentration of reactants does. Shifts the equilibrium. Yeah, that's probably the right way to say it, the equilibrium concentrations. To the right. So it's the same idea, sort of the same idea. It doesn't fall out of the same math, but it's sort of the same idea as we talked about before, whereas if I were to take this and increase the concentration of that, we expect it to move things over to the products. And now we're saying, okay, just as a useful way to remember it, we're going to treat delta H as if it's a reactant. And now if I add heat, which is going to increase the temperature, that's going to shift the reaction over to the right. So all of the things that you would assume based on this are also true. Like if I decrease the temperature, that's going to shift things. Because now it's similar to like if I'm now it's similar to like if I was removing one of the reactants, removing the product, it's kind of the same idea again. And the same is true for exothermic. Let me see if I can pull an exothermic reaction up. Yeah, so like for example, if you're looking at the Haber process, and we say, okay, well, this is an exothermic reaction. That means we can add delta H on the right side because now it's as if heat, or it literally is that heat is being released. So we're kind of treating the delta H like a product of the reaction. It's like if you burn wood or something, you could think of the heat that's being produced as a product of that chemical reaction that you're doing, even though it's not exactly the same thing. Heat is obviously very different from, it's not a molecule. It's this other thing, but this is just a kind of a useful way of looking at it. So now we have delta H in the products, and now everything behaves again like like you expect it to behave if you add product or take away product or whatever from the reaction. So if we increase temperature here, it shifts things to the left. Decrease temp. It's like removing product, right? Because we're taking the heat out as it forms. It shifts to the right. Yeah, it's kind of an interesting result. This piece right here, that increasing for an exothermic reaction, at least I think it's interesting. For an exothermic reaction, decreasing the temperature actually shifts you to form more products. You said like the instinct, I think, and there's other reasons to heat a reaction aside from equilibrium, but like when you're running a reaction, the feeling is like heating it generally helps it to go. And that's true in terms of kinetics. But if you look at and generally, I guess, in terms of kinetics, but if you look at the equilibrium, you can see that if you want to form, if you're running a reaction, you want to form the maximum amount of products. Once you get to equilibrium, you have to concern yourself with whether it's exothermic or endothermic. So for an endo or an exothermic reaction, you actually want to cool it, and you'll form more products by cooling it, which is, I don't know, somewhat like a little bit counterintuitive, I think. Generally, heating things helps reactions to move forward, but that's usually a kinetic thing, which is separate from the thermodynamics, which is what we're talking about here. I guess the last thing to talk about with Le Chatelier's principle, this is kind of beating this thing to death, but it comes up every now and again, is if you have a, well, let me think about how to phrase that. If you increase the pressure, so if you have so let's say that you have a cylinder and it's fitted with a piston right here. So you can kind of move this thing up and down if you want. And I'm running my reaction in there. So I'm running this. reaction. These are obviously gases. So there's two ways I can mess with the pressure here. One is I can move my piston down, but that's going to cause the volume in there to decrease as well. If I decrease the volume, then we know that, let's see, so if we decrease the volume, if we decrease the volume, we know that the reactant is going to shift to the left because there's less moles on the left. Yeah, that's a useful way to think about that. So increasing the pressure by like moving the piston down, which essentially decreases the volume of the system, is going to shift things in this direction. It's going to shift things to the side with less moles, essentially. But if we increase the pressure in sort of a different way, so instead of like changing instead of having to change the volume of the system, which is sort of the typical way you think about increasing pressure, or maybe one way to think about increasing pressure. Another way we could do it though is to let's say you just have a sealed container. So this thing's just sealed off. The other way you could increase the pressure inside of the container would be to, like, let's say you had like let's say the top of this thing was some sort of rubber or something. So you can put a needle in there and pump in some sort of inert gas. So I can fill this up with inert gas. So now I'm keeping the volume. Yeah, decreasing the volume increases the pressure. Yeah. So in this situation, in the situation we're looking at now, we're keeping volume constant. So if the volume is constant and we're pumping inert gas in, we're increasing pressure well, so more pressure. So the way to think about the top situation is really the thing that drives it to the left is that somebody asks us, so more pressure shift left. If you're trying to boil this down to just some simple rules, the real way to think about it is decrease of volume shift left for this particular reaction. It does also increase the pressure, but that's not what actually causes it to shift. And we're going to see that right now. The pressure doesn't actually, shifts to the side with less moles. It's the right way to say it. The pressure actually isn't what's causing the change there. If we increase the pressure by adding inert gas to a rigid container, so things aren't going to change at all. So now I'm adding in more gas into this system. I'm keeping the temperature constant, so the temperature's not changing. And so the pressure in there is going to increase because now I've got more crap in there. This is, let's see, I'm trying to think like, it's the same, it's sort of the same as if you're like pumping a bike tire. That's essentially what this is, right? So we're pumping in air into this thing. Unlike a bike tire, the volume's not changing, but I'm just putting gas in there. So I'm pumping air in. So I expect the pressure in there to increase, even though the size of the chamber is not going to change. What effect do we expect that to have on the equilibrium? So before when we were changing the volume, we had this effect where the volume for the numerator would change faster than a denominator. And this caused the values of the concentrations to change so that they could stay equal to K. But if I just increase the partial pressure of another gas inside of there, which is essentially what I'm doing, it's like, let's say I'm adding in argon gas, which is completely inert. Nothing happens to the partial pressures of NO2 and NO2O4. So remember that the total pressure of a system is going to be equal to the sum of the partial pressures. And that the equilibrium constant, at least when you're talking about in terms of gases, so Kp here, that's going to be equal to the partial pressure of the product over the partial pressure of the reactant. So argon, because it's inert, isn't involved in the reaction. So you'll notice that it does not so it isn't involved in the reaction. So it doesn't appear in the equilibrium expression. Because remember, we're writing out equilibrium expressions for reactions. So naturally, argon is not part of the reaction. Otherwise, we'd have seen it already. We're writing out the equilibrium constant for this. Whether there's argon around or not, we don't really care. So yeah, so this doesn't enter into that equation. And so what ends up happening here is nothing. Nothing happens here. Because I can increase this number as large as I want. It changes the total pressure over here. So increasing this will change the total pressure, but it doesn't actually have any effect on the partial pressure of N2O4 or the partial pressure of NO2. And so because these aren't changing at all, there's no concern of having any kind of re-equilibration to have it stay equal to Kp. So the short answer, the short thing that I'm trying to get at here, which you can deduce from looking at the total pressure or Dalton's law, or whatever that thing's called, is just that increasing pressure using an inert gas has no effect on equilibrium concentrations. I think that's really the last. I think that's really the last. I don't know, like thing that you could possibly think about in terms of Le Chatelier's principle. So I know it's confusing because it ties back in. So here, I just want to draw the distinction. And usually, I think if it's phrased in a question, you'll know that the volume is changing. If I change the volume here by applying pressure, sort of in the like the kind of almost like the traditional sense of thinking about increasing the pressure, where you just sort of like take a piston and like in a car engine or something, where you take a piston and you just sort of compress the gas through a compression thing. There, because you're decreasing the volume, you actually do affect the equilibrium. In this sort of less familiar case where I increase the pressure by just kind of pumping in another gas like argon, there I don't see any kind of change in the equilibrium concentrations because I'm not actually, I'm not changing the volume of the system or the temperature of the system. So yeah, there's like a 1, 2, 3, 4, 5, 6, 7, 8, 9 different things that you could kind of conceivably mess with for this is a nice, I don't know, for, you can apply these to lots of different reactions, but if you kind of understand what's going on in this, you just need one reaction if you're making like a crib sheet or something. Let's see. So we can, I'm trying to think of how to structure this. I don't know that there's a good way. You can add N2O4, or we could add NO2. You could remove N2O4. We'll write over here that this is endothermic. You could remove NO2. We could decrease the volume, increase the volume. We could decrease the temperature. We can increase the temperature. And then finally, we can like, I don't know how to phrase that. Let's just call it add inert gas. This increases P. So if we add inert gas, and so we can think about like what actually happens here. So if we add NO2O4, what's the shift going to be?
To the products.
Oh, good. Yep, shifts to the products. I'm going to say shifts to the, yeah, shift. Sure, let's call it to products. Oops. Let's just say products. Actually, since I'm going to be writing that over and over again. And if we add NO2, then we're going to shift to the reactants. If we remove N2O4, let's see, that's going to shift to reactants. If we remove NO2, that's going to shift to products. Let's see, so if we decrease to the volume, that's going to shift, again, away from the side that has more moles. So it's going to shift to reactants. Increase in volume is going to shift to products. Since it's endothermic, if I decrease the temperature, that's going to shift to reactants because it's like removing a reactant. It's similar to removing N2O4. Increase in temperature is going to have the opposite effect. It's going to shift it to the products. And then finally, if we add inert gas to increase the pressure, we just don't see any shift. So there's like a reasonable density of stuff that you can ask about this, but it all kind of falls out of the same idea. I'd say the ones that are like a little bit, and they're not super hard. I guess you can like, for this one, like decrease volume or increase volume. Those I usually have to think about for a second, but you can also just remember that it always shifts to the side. So if you're decreasing volume, it's going to shift to the side with less moles. If you're increasing volume, it's going to shift to the side with more moles. I usually write out K for that and think about it for a second, but you don't have to do that. And then, yeah, these are a little bit weird as well, but as long as you can remember which side of the reaction the delta H goes on. Endothermic, it goes on the reactant side. Exothermic goes on the product side, and treat it as if it's a reaction or product. That's not so bad. And then this one's like the least easy one to just kind of like be like, oh, right away when you look at it. So you can either just remember that if you add inert gas, it's not going to actually do anything, assuming that the container stays rigid. Or you can take a look at like Dalton's law and sort of rationalize that yourself. Yeah, so if it's exothermic, so there's a couple of things that can change this. So if this is true of this specific reaction. If it were exothermic and endothermic, then this would be flipped. Yeah, sorry, if it was exothermic and not endothermic, then this would be flipped over. If you had like, let me see if I have another reaction here. So if you had another reaction like the Haber process that we were looking at, this would be a good one to kind of go and make sure you can kind of fill out one of these tables for. I don't know that we would ask you to fill out a table. I mean, I guess this would lend itself to Canvas, but I don't know that we would ask you to fill out an entire table for this. But if you can, then you can obviously say, you can obviously answer any of the questions related to Le Chatelier's principle. At least anything that we ask that's kind of straightforward like this, which I think is probably how we'll ask them. So yeah, you could go in and say like, what happens if I add N2? What happens if I add H2? What happens if I add NH3? What happens if I remove any of those? What happens if I increase the volume, decrease the volume, decrease temp, increase temp? The only thing to remember is that the only other thing I'd say is like, if you're dealing with solutions, these two things, decrease volume, increase volume, don't really make sense anymore, because I think this is obvious, but I'll say it again. I'll say it just because some things I like, if you haven't worked in a lab, some stuff just is not, some of this stuff is not super obvious just because you're not used to thinking about it. But if I have like a flask, let's say an Erlenmeyer flask, and that's got 1 liter of solution in it, if I take this and, pour it out, let's say this is a 2-liter flask with 1 liter of solution in it. If I put that into a larger flask, so let's say now I've got a 5-liter flask. Okay, yeah, like my solution thins out a little bit at the bottom because it doesn't have as much volume, but I still just have 1 liter of solution there. So changing the volume of container here doesn't do anything. That doesn't actually have any effect on, there's no effect on equilibrium. And why is that? It's because the concentration, it's kind of like if you take so the effect of changing the volume, if you have a gas in there, is it dilutes it. With a solution, though, there's no dilution that takes place by changing the size of the vessel. So, if you have like Gatorade or something, and you take it, you have like a 50 milliliters of Gatorade and you take it and you pour it into a larger glass and drink it, it tastes exactly the same. It's not like you've diluted it by just pouring it into a larger volume. That's basically all we're stating here. With gases, it's different because gases they fill the entire container that they're in. So if I'm in like a 1 liter beaker and I have 1 mole of gas, my concentration of gas there is 1 mole per liter. It's sort of like the vacuum of space is the solvent, and you're sort of containing that vacuum of space within a rigid body. So if I take this and double it, let's say, now I have a 2-liter flask. I still only have 1 mole of gas in there, But unlike with the solution where it stays at the bottom, so like here it's like, okay, I've got the solution. The solution is sets the concentration. That liquid isn't affected by the change in volume there. Here, for the gas, it's going to expand to fill this whole thing. And so now we've got 2 molar versus 1 molar. And so changing the volume of that affects it'll affect the equilibrium for it. So but basically what I'm saying is for solutions, it doesn't matter. If you want to like emulate the increase in volume and decrease in volume that we see here, with a solution, we actually have to go in and add more solvent. So if I took this, and I wanted to actually do the same thing as like right here, where I sort of half, or sorry, it's actually backwards. Yeah, 0.5, sorry about that. If I wanted to half the concentration, yeah, what do I have to do? I have to double let's say this is in water. I have to add another. I guess since I said that's a 2-liter flask, I would, fill this to the top. Now I have 2 liters of solution. And now we're going to see basically the same effects that we see when we change the gas, the size of the gas container. Like, so I guess another way of saying it, instead of saying the gas container, the solvent is the vacuum of space, which sounds, I don't know, kind of heady, is when you're dealing with a solution, it's like the solution, the solvent itself is like a container, is the container that the reaction's taking place in. So whereas with the gas, the container is very straightforward. It is literally a container. It's the flask that you're in. For a solution, the container is the solvent itself, which in this case I've drawn as water, but it could be anything. But it happens inside the liquid. But yeah, that's pretty much Le Chatelier's principle.
Why does it with gas? Why does it shift to the side with less moles?
Moles. Yeah, the shift comes from. So the question is, if we have a gas, why does it shift to the side with less moles? And the reason is, let's see where I can cram this in at. I'll just copy it. The reason comes out of looking at the equilibrium constant. So it's this number is fixed, so it doesn't change. I don't know what it is for this reaction, but it's not going to change at all. If we write this out as, so if we write this out as nRT over V, the concentration in the numerator is going to change as the square, because that square is going to apply to the volume term, whereas down here, the concentration is just going to change to the first power. It's going to change linearly. And so the concentrations here are going to change differently as I expand the volume. So as the volume of my container increases, let's say from 1 liter to 2 liters, the way that the sort of the reactant itself or the product itself is going to experience it is going to be dictated by whatever this term is. So for NO2, it's experiencing the volume expansion sort of as a square here. And so this number is going to get smaller. This top number is going to get smaller faster than the bottom number is going to get smaller. Or I guess you could say the magnitude of change, maybe that's a better way to say it. The magnitude of this change in volume will be larger. So because V is the same for both of these, because they're both in the same container, what we're going to see is, I'm trying to think of how to pull this all out. Yeah, I guess what I'm thinking is, like, since V is the same for both of these, so V is equal to 2, in the numerator up here, that's going to end up being a 4. And so it's sort of like you're taking the number of moles that you have in the NO2, which is the product here, which is the, has the excess of moles, and you're dividing it by the square of the volume. So its concentration goes down more. Is that the right way to say that? It's concentrate. I guess it's the term in the equilibrium expression. This I at least know is true. The term in the equilibrium expression for the partial pressure of NO2 decreases much more than the one down here, because this one just goes to the first power. So this will be halved, whereas this will be fourthed. And so now you're changing the ratio of the numerator to the denominator, and since you're changing that ratio, that means that K, but K isn't changing. These two things are going to have to come back and finally find the original ratio that they had before you change the volume.
Okay.
So yeah, so not as short of an answer as I wanted, but yeah, the volume changes. But basically, the effect is just that if you have it has to do with the coefficients that come out here and how they come and appear inside the equilibrium expression. So if the coefficients are the same, then everything changes the same. So if it was a square term on the left side, then we wouldn't have to worry about it because both would be changing. So yeah, but you can play around with the equilibrium expression and kind of pull that out of it. Okay, so yes, we got a little bit of time left. Let's see, what else can we talk about? So we'll finish up whatever this stuff on Monday. I don't know how. I'm still working on the exam. I'm not sure what questions we'll have exactly on this, but they won't be the equilibrium expression type stuff. Not even Le Chatelier's principle. I don't think that stuff is super hard. But the equilibrium expression stuff is probably some of the harder material on there. We'll give you a good idea of, I think, how many questions at least before the exam day, or what the distribution of the material will be. Let's see. So we have these other equations that we can look at. Let me try and think about this. So yeah, so K it's related to the free energy of the reaction. So if we think back to what we know about thermodynamics, we know that for whatever our reaction is that we're looking at, like let's say you have this reaction, these are all gases. So we know that we're saying, like, oh, the extent that this reaction goes to the right, so to the extent that I form NO2 is decided by this thing K. And then we're defining K as the reactants over the products. It should make some sense that delta G is going to be related to this. Because if you remember, like the free energy, or what predicts whether a reaction is going to happen, is the free energy. And so the whatever predicts the extent to which the reaction happens should be related to delta G. And it is. And we can relate it through this expression, delta G is equal to RT, negative RT, natural log of K. So delta G with a knot on the top delta G, what do we call this? Standard? Yes, just standard free energy, or delta G in the standard state or whatever. That's when we're at equilibrium. So under very specific conditions that we can tabulate, that's what the delta G is equal to. So this is the delta G associated with the equilibrium constant K. Yeah, why don't we? I'll save because I don't want to get super deep into this. But why don't we look at? I guess the thing that where I'm going with this is that we also know that from first semester general chemistry, we also know that delta G is equal to delta H minus T delta S. And so the nice thing, or sort of one of the things that you can do with this is, if I know delta H and delta S, then I know delta G. And so if I know delta G, then I also know K. That's what this allows you to do. Yeah, so delta G, somebody asked this, a good question, and we'll cover this next time. Delta G without the knot on it equals 0 at equilibrium. Delta G knot is a different thing. That's the standard, I feel like I'm blanking on the name, but it's a standard free energy. It's like a tabulated value for the free energy associated with that equilibrium constant. And we can talk more about like what that is next time. Say delta G is something else. Or we can say delta G is non-zero. What's that? It's sort of like the difference between K and Q. What value would you use for R? I think R probably is decided by, let's see. Is there, maybe it depends on if you're using a gas or a non-gas. I feel like I should know this off the top of my head. I want to me, it's the 8.314 joules per mole Kelvin is the one, yeah. I'm trying to think if that changes if you use the gas one, if you have to use 0.0821. I'm not 100% sure off the top of my head. But yeah, let's hit this next time. The other question here is, we'll solve a problem or something with this on Monday. But you can see this, I hate to say this, but like this type of thing lends itself to a little bit more plugging. Like, okay, I got delta H, I got delta S, I'll use that to calculate delta G. And then I can take delta G and I can use that to calculate K and vice versa. So these are more like straightforward. I'm going back and forth between a few different equations, as opposed to the Rice tables where it's a little bit more, I don't know, it's just a little bit more wandering. Delta G, I would dictate whatever its final units are by whatever you use for R. So joules, and then you can convert it to kilojoules or something afterwards if you want to. But generally, I don't mess with the whatever R is. Yeah, I guess R should be 8.314 because then you end up with actual energy units for delta G. So, all right. Question about the exam is, what do the test questions come from the worksheet? Let's see. I think the worksheet is a good guide for the questions. Remember, the worksheet doesn't actually cover any equilibrium stuff, so you want to look at the GChem worksheets for that. But yeah, I think the worksheet questions are generally what we're kind of looking at or looking for. There's also an old test or something similar to an old test on the review sheets. Those are also a good place to look for questions. But yeah, we'll try to give you. I'm not always perfect at this because sometimes I think things are obvious and they're not. But we try to give you questions that are similar to questions that you've seen. you got a little bit more time and it's open book and stuff. Uh, that might shift things over a little bit in terms of how we ask the questions, but we're not going to try as a teacher, I think in general, I try not to give questions that are not similar to questions that we've already shown you. Not that you shouldn't be able to extrapolate. I just think that's a lot. It's a kind of a big ask on an exam when you're first learning information. So expect the things to be consistent with the problems that we've shown you, and anything that's not consistent shouldn't be like mind-numbingly difficult.
Will it be a mix of fill in the blank and multiple choice?
I think we'll probably just do multiple choice just because the fill in the blank always gives a lot of problems on Canvas if you're off by like a certain numerical value. So we'll probably give you lots of multiple choice questions just for simplicity's sake on our end and on your end. But yeah, so we'll send out something. I'll probably make an announcement about the exam over the weekend or something, and then on Monday we'll finish up some stuff, and on Wednesday we'll do a review. The only topics that you don't have to know, for my class at least, is we didn't do anything with the Clausius-Clapeyron equation. So any kind of calculations involving changes in pressure. Changes in, what is that one for? It's changes in pressure and how that affects the boiling point, and being able to relate that quantitatively. I won't have any questions on there regarding that. There's maybe one other law like that, but the Clausius-Clapeyron equation is the obvious one. But other than that, everything we covered will be on the exam. So, I'd say the other thing that you don't have to worry about, I think it's question 17 on the review worksheet, where you take an ice cube and you let it melt into water and you try and calculate the final temperature of everything. That problem was a big pain in the ass for me when I was getting office hours. So it's not a bad problem. It's kind of a fun problem to work out, but it's just a little bit, I think it's probably too long for an exam. So I wouldn't worry too much about that. If we give you something like that, it'll be much more simplified version of that. Other than that, if there are any updates, I'll send them out via email. Via an announcement via Canvas. And you'll have your opportunity. I'm sure a lot of you guys are just getting started studying over the weekend. You'll have an opportunity to ask more questions, probably on Monday, but definitely on Wednesday, if you need like help with straightening certain aspects of the concepts out. And then naturally in office hours, you can ask whatever you want. So otherwise, enjoy your weekend when you finally get done with classes today. And yeah, see you guys next week. Hope you guys have a good time studying, whatever that means. Bye, guys.